Hello, good morning. We're live and I'm happy. So, we're going to quickly cover. I want to go through the whole chapter 8 for you to just finish it one time and do a whole lot of questions with all of you. A whole lot of questions from past papers, and we make sure we are done with chapter 8 for our Cambridge checkpoint science. Can you both hear me? Can you all hear me? All right. So, let's push and let's make sure that we can quickly cover it. Now, what we know is that our checkpoint science has how many chapters? Yes? We're going to do 8.1 and 8.3 since we just did 8.2. We can talk about it a little bit though. Checkpoint science. Our checkpoint science has how many chapters? 9 topics, right? We know that our checkpoint science, stage 9 science has 9 topics. Now, of those 9 topics, we know that you have 3 for bio. And then you have how many for chem? You have 3 for chem. Then you have 3 for physics. This makes 9. So these are the 9 chapters for checkpoint. 3 are for bio, 3 are for chem, 3 are for. The 3 chapters for bio are chapter 1, chapter 4, chapter 7. The 3 chapters for chem is 2, 5, 8. Then the 3 chapters for physics is 3, 6, and 9. So we are looking at chapter 8 for chem. Okay. Chapter 8 is chem. That's the one we are looking at, which is called rates of reaction. Chapter 8, as I've just shown you, is a chemistry chapter. And it's called rates of reactions, and that's the one we are looking at today. Now, the first thing you must know, this chapter is broken down into 3 things. The first one is we want to know rates of reactions. First thing we must know, remember we said it's broken down into 3 things. First thing we must know is what is the rate and how do you measure it? What do we mean when we say rate of a reaction? Okay, for stage 9 chemistry students, what do we mean when we say rate? So all stage 9 students should know what do we mean when we say rate and how to measure. So the first section we can say it is about measuring the rate of a reaction. We need to know how do you measure. Then the second thing is what effect does surface area have on rate? That's the second. The second section is how does the rate change when you change the surface area? Then the third and final thing is how does temperature affect rate? So first thing we see how we measure the rate. Then we see how the surface area affects rate. Then we see how the temperature affects rate. Then we are done. Okay? Those are the 3 sections that you must all know. Give me a second. All right, so what we were saying is, right, we need to know these three sections for us to say we know the rate. We need to know these three sections. Have you seen the three sections that we need to know for us to say we are done with the chapter? You need to know how to measure the rate, right? Say it after me. You need to know how to measure the rate. That's the first thing. Say it. The first thing is to know how to measure the rate. Mr. 80, the first thing is to know how to measure the rate. Then when we know how to measure the rate, then the next thing we should know is the effect of what? Surface area on rate, right? Then the last thing is the effect of what? Of temperature on the rate. Okay? Now, how do you measure the rate? Here is a setup that is going to be used a lot. So, this is going to be a flask, which we call it a conical flask. It's called a conical flask. So in here you have put your reactants. Here, this is your acid. Then you drop a metal, a ribbon. This is a magnesium ribbon. It goes in there, it starts producing a gas. The gas will rise and go up and go into the syringe. This is a syringe. And the syringe will be collecting the gas and measuring it. Are we together? So this is what you're going to be learning. You learn how to measure the rate. How to measure you'll be having a timer, you'll be having everything, and we'll talk about it. So let's put the introduction. What you must know is that because we are trying to study how you measure the rate of reaction. So let's put a background so that everybody knows what we're talking about. What you must know is when we are saying we're measuring the rate of a chemical reaction, you should know that every chemical reaction takes time. Every reaction takes time. Okay? It just doesn't start and finish in one time. Okay? It has some time. Now the time may change. Okay? Some reactions happen very fast, like almost instantly, like it's done. While others may take hours, others take days to finish, others take years to finish. So reactions take time. Are we together? Reactions take time. And the time that a reaction will take is different for different reactions. So reactions take time. Now, scientists want to be able to know this reaction takes this long. Scientists want to know. They want a way that they can use to compare different reactions. Okay? How do we have tell us the speed at which the different reactions are happening? So we want to say, this reaction is very slow. This one is fast. Do you understand? And for scientists to be able to do that, they need to be able to measure something called the rate of a reaction. Scientists, do you want to be able to measure and compare different reactions? Yes, we want to be able to. So you need to measure the rate of reaction, scientists. If you measure the rate of reactions, you can compare the reactions. So this will help them. We'll be able to now know, this reaction happens at this rate happens. And then we can start to now learn the different ways that we can use to increase that rate. Are we together? Are you hearing me? If we can measure the rate, we can start to find different ways to improve that rate. Are we together? Good. So, here, understanding it will help scientists to improve these reactions. Industrial processes just means reactions. Reactions that are used to produce food, to produce medicine, to produce everything. So what have we just said? We said if you're a scientist, you must know how to measure the rate so you can know how to improve the processes, how to improve manufacturing of medicine, because there are reactions happening there, how to produce food more efficiently, understand resting, understand digestion, understand all these things. Are we together? So, how do you do it, Mr. Scientist? How do you uh, find the rate of a reaction? Because we have seen here why you must measure the rate of reaction. Because if you measure the rate of reaction, you can compare different reactions, the speed at which different reactions are happening. And when you compare them, you can start to improve. Come on, don't let me down. So you can compare and improve the processes, the reactions, whatever. All right. So rate of reactions, here's the thing. The rate of a reaction depends on the number of successful collisions. So anyway, before we start, did you see why we must measure the rate of reaction? Why must we measure the rate of a reaction? Why is it so important for us to do it? Why are we doing this? Are we wasting time? Why is it that we don't just react things and we let them react, then we just go away? As Form 2s or Stage 9 students, why would we come back to start and try to see how fast it is happening? Why is it that we don't just mix and go away? If you do that, you won't be able to know how to improve processes, right? You won't be able to know how you can produce food better. How to produce cheese better. You want to produce more cheese and stuff. You won't be able to know how to do it because you don't know how to improve it. If you want to know how to improve it, you must know how to see how fast it's happening. You should be checking how fast it's happening and improving that, and then you will be getting a better process. Are we together? So we need to know how fast is this reaction happening so we can start improving it. So let's see how we can do it. We need to check. Let's see how we can know how fast the reaction is happening. Right. Rate of reaction depends on the number of successful collisions. So if you want to have a reaction, you must have a successful collision. If you want to have a reaction, you must have a collision that is successful. Now, if you want to see the speed of a reaction, you should see the number of successful collisions every second. Are we together? How do we see the rate of reaction? We see the number of successful collisions per second. Okay? Rate of reaction means speed of reaction. It depends on the number of successful collisions. Do not forget. Tell anyone who asks you to say a reaction is all about collisions. It's called the collision theory. And a collision has to be successful for a reaction to happen. If we want to find the speed of a reaction, we see how many successful collisions do we have every second. Are we together? How many successful collisions? So, here we are back at it, the background. Chemical reaction is a process in which one or more substances change into new whatever. This is just what a chemical reaction is. Well, we know that for a reaction to happen, what must happen, students? What must the reactants do? The particles of the reactants must do what? What we just saw. They must. For us to have a reaction, we must have what? We must have a collision. For us to have a reaction, we must have a collision. What type of a collision? A successful one. So these reactants that you have, their particles are colliding successfully, and they cause them to react and form new substances now. So, okay, a process in which a substance is changed into a new substance is a reaction. Now, here, rate of reaction, we said it is the speed at which reactants are converted into products, or the speed at which, or the number of successful collisions per second. Because a successful collision is a reaction. So the speed at which the reaction is happening, or the speed at which reactants are being converted to products, this is the rate, the speed, how fast a reaction happens. Rate is all about speed, rate of reaction, how fast a reaction is happening. Some reactions are fast, some reactions are slow, like we said. Fast reactions, fireworks. For fireworks to explode, there is a reaction there, and it happens so fast. Then it goes, it goes up in the air, it explodes. You see nice lights and everything. This is a fast reaction. Burning petrol is a fast reaction. You can finish your fuel driving from here to the next place. Your petrol will finish because it's happening fast. Neutralization reactions here, then vinegar with baking soda. All these are fast reactions. They're slow reactions. Rusting is a slow reaction. And rocks, weathering of rocks, the breaking down of rocks. So all these are slow ones now. They take months and days and whatever and years. Okay, and the ripening of a fruit, it's a slow chemical reaction. Are you seeing this? So the time it takes for a reaction to happen is the rate of a reaction, or the number of successful collisions. Per second, by the way. Now, why is it important? We said, why is the rate important? So that we can improve processes like manufacturing medicine. Okay? Medicine must be produced efficiently and safely. You must produce it as fast as you can, but also safe. And that is why you need to study rate and see what are the ways in which you can produce medicine quicker. Come on now. You cannot ignore this. If you want to be a scientist, you should be useful. Your science must help us. What good does it do if you know science but you cannot help us? This is how you can help us. You must know that, Mr. Scientist, the reason we want you to know this is we want you to be able to produce medicine as efficient as you can. Food, you should produce food as quick as you can without burning. Fuel should burn quickly. If you can quickly burn fuel and make energy, that means the car is a very, very powerful one. Those nice, expensive, powerful cars, they have good, strong engines. Give me a second. Right. Did you see this? Can we continue? All right, good. So, what the last thing which we had said was that the rate of a reaction is very important because we have practical things. Engineers, metals must be protected. Should galvanize them. We'll talk about how to protect. But for you to know how to protect, you must have studied rusting. And how the speed at which it does it, and you can protect to make sure by the time rusting wants to happen, you have protected your metals, right? Let's say you build a bridge, huh? Let's say you build a bridge, then the iron you used to build a bridge starts rusting. The bridge will collapse. Do you understand? You need to build a bridge and protect the iron so that it doesn't rust. So, rate is important because we have several practical reactions that we must know. Cooking, car engines, how to make a car move faster. If you want to make a car move faster, you should make it react faster. So that means you should have studied the rate. For you to know how to improve the rate, you should first know how to measure it. So when you are measuring it, then you can start to improve it, and you'll be checking to say, is it actually getting faster? Because you are measuring, okay? If you don't know how to measure, then how will you be able to know if you are improving or not? There is no way. If you want to be able to know how to improve a reaction, the rate of a reaction, you must know how to measure it. Are we together? What did I just say? I said, if you want to improve the rate of reaction, you must know how to measure it. Okay? So that you can measure as you are improving and you'll be checking. So, anyway, here are some signs that you can use to know if a reaction is actually happening. So, first thing we should know is a reaction taking place? If it is taking place, now we can start to measure its rate. And here are things that can happen. If a reaction is happening, you can see bubbles. If you see bubbles, just know a reaction is happening. Okay? If you see bubbles, just know a reaction is happening. If you see colors, the color changing, a reaction is happening. If you see a solid disappear or a solid forming, that means a reaction is happening. If you see the temperature of a reaction changing, that means the reaction is happening. If you see the smell changing, so smell, temperature, solid can form or disappear, color can change, bubbles can form. All these are signs that a reaction is happening. And how we can measure the rate is we can use a syringe or a balance or a stopwatch. These are not or syringe and balance and stopwatch. These three, we need them. These are the methods that we can use them. When you use a syringe, you'll be measuring the volume of gas produced. If you use a balance, you'll be measuring the loss of mass. I'll teach you. If you use a watch, this is what happens when you get to A level. You're going to be doing a reaction in the lab. When you get to A level, you're going to be doing a reaction in the lab, which is called a titration. So in the titration, you'll be having a gas, sorry, not a gas, an acid and a base. And you'll be mixing them. There'll be what we call an indicator. So you mix. When they get to a certain point, you're going to see a color start to form. You see a pink color. If you use phenolphthalein, then you see a pink color in your solution. Then you quickly stop the reaction. You quickly stop the time. So this is one way. So if you see a color change or something, you stop your stopwatch. If you are using mass, you see loss of mass. Okay? Or the volume of gas. These are ways to measure how fast a reaction is happening. Because if it's loss of mass, we'll see how much mass was lost per minute or per whatever, per second. Then we can be able to know the rate. If a gas is formed, we see how much gas was formed per second. how much was formed per second. So you divide the amount of gas produced by the time it took, then you know the rate. For mass, you divide the mass that has been lost, or the mass that has appeared. You divide by the time in seconds. Or you're going to wait for a visible change and you see how long it took. Here is one. Method one, which we said, measuring using checking the rate of a reaction. So these are the how we can measure the rate of a reaction. So let me say something. Form 2s. One of the most important things when you're studying a chapter. Yes, we have been talking about importance of these. What is rate of reaction? Why is it important to know the rate and all this? Okay, fine. Well done. You now know those things. But that's not the main thing. The main thing is what we are doing now, which is how do you measure the rate? What methods do you have? Gas range and balance and stopwatch. 3 methods. All 3 work. All 3 work. You can use a gas range to collect gas, and you check the volume of the gas produced, you divide by time, you have the rate. This one, for a gas range, you use it when the reaction is producing a gas. If the reaction is producing a gas and you want to check the rate of reaction, please do this setup. Setup for gas range, this one. When a gas is produced, you use this method. Are we together? Now, if a gas is escaping into the air, then you can use the balance like this. If you don't have a rubber to stop the gas escaping and everything, you can now use this. In here, you can see that the gas is going into the air. So it's being lost. We are not collecting it. That's fine. Really? What? Yes. What? So how will you find the rate? You see how much the mass decreased. Are we together? You check the mass, how much it decreased, and you divide by time. So this is important. Measure the loss of mass. This is the second way to measure the rate. Are we together? When do we use the mass on a balance to check the mass loss? When the gas is escaping into the air in our reaction. Then you can use the stopwatch method if you can check the time that it takes for the visible change to happen. Stopwatch, you use it when a color change or a precipitate is being formed. If your reaction is going to form a new color, like this reaction, a very, very, very popular reaction. So what you do, listen, you lift this flask and you put on top of the X. And when it starts, you'll be seeing the X. But as the reaction keeps happening, the X begins to disappear. So you can no longer see it. The color has disappeared. The black cross has disappeared. Once it fully disappears, you can stop your reaction. Are we together? This is the third way of checking the rate of reaction. Are we together, students? If you use the gas range as the first one, what do you do with the gas range? When do you use it? You use it when the reaction is producing a gas. You collect the gas in a gas range. Then you'll be checking the volume as time is moving. then you are going to just divide to see the rate of reaction. What is the advantage of using this method? It will give you accurate measurements. It is easy to read, and you get nice continuous results, because you'll be checking the volume after maybe every 10 seconds, 10 seconds, and you just keep doing that. You don't have to stop the reaction and redo it or anything like that. Here, this method, you can only do it if you have a reaction that produces a gas. If you have a reaction that does not produce a gas, then how can you use this method? There's no way you can't use it. So there we have it. Second, measuring loss of mass. So as the gas escapes, then mass is lost. Are we together? So this is what happens. The total mass of the flask will decrease. Okay? The faster it decreases, the faster the reaction. I'll show you. But if the mass is changing, and by changing we mean decreasing, because it is losing some stuff. If the mass is decreasing, then we know a reaction is happening. All right. Now here, the one for time. For time, we said you look at physical changes, visible changes. You check how long does it take for a visible change. Have you seen this? When you have a visible change, then you must use this method, okay? Measuring time. Okay, these are especially for a reaction where a gas is not produced. So the shorter the time it takes for a visible change, then the faster the reaction. Have you seen this? The 3 ways of measuring rates. What is method number 1 of measuring rate? You use a what? A gas range. When should you use that method to measure the rate of reaction? The gas range? When your reaction produces a gas, right? Good. When the reaction produces a gas. What about method number 2, Mr. AT? What is method number 2 of checking the rate of reaction? Have you seen this one? We said method number 2 is you do what, Mr. AT? Mr. AT, what do you do in method number 2 of checking the rate? Checking the what? The second method of measuring the rate of a reaction is to use yes. is use the loss of mass. Yes. The second method, we use the loss of mass because the gas is escaping now. So we use the loss of mass to check the. Then the third way is what, Victorson? You check her? Yes, you use a timer to check when a visible change has happened, right? Use a measuring timer to try and find out when a visible change has happened. All right. So now here we come to more collision theory, which we are going to use a lot. Collision theory is just what we already discussed. Collision means things are colliding. And we know that for our collision theory just says that for a reaction to happen, particles must collide. Here, the three conditions needed for a reaction to happen. That's the collision theory. It gives you the conditions for a reaction. The three conditions for a reaction to happen. Number one, particles must collide. There are three things that must happen. Particles must collide, and they must collide with enough energy, and they must collide in the correct orientation. If one condition is missing, reaction will not happen. You want a reaction to happen? Three things must happen. The particles of the reactants must collide. There is no Bluetooth reaction. The particles must collide. And they must collide with enough energy. Low energy collisions do not produce a reaction. Particles must collide or meet. If they don't, no reaction can occur. Then particles must collide in correct orientation, in correct position to form new bonds. If the orientation is wrong, then they cannot fit in, they cannot form a new bond. Are we together? This is what we call the collision theory. Anyone with a question? So, what is the difference between a successful and an unsuccessful collision? An unsuccessful collision, it's so for us to say we have a collision, that means the condition number one has been met. Particles have collided. But we said all three must happen. They must collide, and they must collide with enough energy and in the correct orientation. So, unsuccessful collisions, particles may collide, but they may not have enough energy, or they may be in the wrong orientation. So, no products are formed. Unsuccessful collisions, the particles collide, but they don't have enough energy. And they don't have the right orientation. That would be an unsuccessful collision. We need a successful collision for a chemical reaction. For a successful collision, three things must happen. The particles are colliding, yes, and they must also collide with enough energy and in the correct orientation. Are we together? Now, here is more. What people must now know is we've talked about collision theory. Here we are talking about a separate idea. Okay, we are doing idea one by one until you now know all the background information. Reactions, when they start, they're going to be very fast. Reactions, when they start, they are very fast because there is a large concentration. Large concentration. Large number of reactants. at the beginning of a reaction. There are many particles. So you have a lot of collisions, a lot of successful collisions, and the reaction will be fast. This is when a reaction begins. You have a lot of particles. There are many particles. You should be able to explain this. There are many particles, which means there are many collisions and many successful collisions, which means the reaction is fast. But as the reaction keeps going on, the number of particles in the reactants will be going down. So you now have fewer particles, which means fewer collisions, which means fewer successful collisions, which means the rate of reaction becomes slower. As the reaction goes on, it slows down. Okay? The reaction will slow down until it eventually stops. Questions? Yes. It's like this. Yes, we did, but I did not show you these. So that is why I'm doing these slides and stuff. Look at the rate. Or let me say, the rate is going to be the slope instead of this. This is the rate. Okay? This is the rate. This is products. We are saying the amount of product is formed. Look at the rate. The rate is the slope. Look what's happening to the slope. It's going flat, which means the rate is reducing. Because the rate is highest when it's steep here. Reaction, fast reaction here. That's the first stage, fast reaction. Fast reaction is when you have a steep slope. Steep slope, fast reaction, which means it's so hard to climb straight going up like that. Now, as the slope begins to become more and more gentle like this, the reaction is slowing down. So reaction is slower. It's curving, going flat. Then finally, when it's flat like this, the slope, listen, the slope is the rate. So the topic we are doing today, students, is the slope. We are doing rate of a reaction, the speed of a reaction. We look at the slope. When it's steep means it's going up. It's nice and hard to climb. This is a fast reaction. But when you see it begin to fold like this, reaction is becoming slow and reaction completes when it's flat. Are we together? And here is not rate. This is the amount of gas, the volume of gas produced. Are you seeing? Remember, it's the same things I've been saying. A steeper gradient means faster reaction. So this one in red is more steeper than the one in green. The one in green is not very steep at the beginning of it. So it's a slower reaction. The steeper you get, which means the harder it is to climb by. Have you seen this? Steep gradient. Not line. Steep gradient, the slope here. The steeper, fast. So the reaction on top here is faster. This is the faster one, and this is the slower one because the gradient is not as steep. Okay? Then when reaction finishes, you get a flat line like this. It'll be flat. All right. Now, have you seen it? How do you calculate the rate of reaction? You look at the amount that was produced and you look at how long it took to produce it. You divide, you have the rate. Okay? All right. Now, let's say you are measuring the rate and you are putting your graph. We'll talk about how to sketch a graph. And let's say you get a value which is going to be here. This is what we call an anomaly. This is called anomaly. So, anomaly is an anomalous result, a result which is different from the others. Now, make sure it does not fit into the pattern of the others. The other ones will be like this, it will be alone. Okay? Now, it should be alone. What causes these anomalous results? If there is an incorrect reading, faulty equipment, human error, and all that. So just make sure. Yes. Yes, it's the odd one out. A weirdo. If you read the values wrongly, or you use a dead device and equipment, or some other human error that could be there, like you affect something when you're reading, then that means you get an anomalous result. But remember, don't fit it into the other pattern. Okay? So, anyway, this is enough. I'm happy with what it is. Don't forget rate of reaction, what it is, and how to measure it. Here it shows you the last how to measure it. The same things we talked about, a flask, a syringe, and whatever, and you be having your tube go out of the flask. So you can put it like this. Goes to your syringe. Here is a syringe. So this is what you do. Then you put your ribbon inside and whatever, then the bubbles go up and they go into. So this is how you measure the rate. Right. Anyway, explain using collision theory. Don't forget, particles must collide. Um, and because they must collide, when you have more successful collisions, then your rate will increase. When you have more collisions, you have more successful collisions, and your rate will increase. We want to see that. Anyway, this is good. I'm happy. I'll give you this to go through the last parts, the common mistakes and whatever. But are we fine here? On a graph, we know that the rate is the slope. We know that reactions slow down over time. When reactions start, there are many reacting molecules, and there are many collisions, and there are many successful collisions, and the rate is high. As the reaction continues, reactants gradually get used up, fewer particles remain, fewer collisions occur, fewer successful collisions occur, rate of reaction is slower. Anyone with a question? Who has a question on this so far? Who has a question?